Okay, in this lesson, we're going to go ahead and do some new trigonometric things. And we're going to take a look at the law of sines and the law of cosines. We're going to derive them out, and we're going to see how to use them in a rewarding way here. So, things that we're going to be learning is how do I use the new school super terrific way to calculate the area of a triangle? How do we use that new school super terrific formula to derive the law of sines? How do I use the law of sines, and what are its pitfalls, and what is the law of cosines, and how do I use it? Okay, so let's just go ahead and jump right in. But before we do that, let's take a look at some things that we might need to go ahead and get under control before we start. Okay, so the first thing that we want to do is that we want to make sure that we're labeling triangles correctly when we're doing some problem solving here. And so what we do is that if I have a triangle ABC, it is customary, or it's kind of like standard practice to all the angles be the uppercase letters and the sides that are opposite from them be the lowercase counterparts. Okay, so anytime that we label some problems and such that you're going to see in the video and some of the other activities that we're going to practice, that's what it's talking about, okay? To go ahead and label these sides the opposite. So, like that guy. Okay. So, at any rate, we also want to be able to break a triangle up into some parts and calculate its area in an old school type fashion. So, what I want to do is that I want to take a look at the area of an equilateral triangle, and I'm going to call each one of these triangle sides. And so therefore, they're all equal length because it's an equilateral triangle. And what I want to do is that I want to find the formula that is going to go ahead and give me the area of that triangle just by knowing one of its sides. So let's go ahead and take a look at how we can knock this thing out. Okay. So the first thing that we want to do is that if I got an equilateral triangle here, I'm going to draw in a height here, and we're going to need, so if I look at the original way, area equals base times height of a triangle, and I want to get rid of the b variable and the h variable, okay? And s right here is going to be the base, the side that thing is on. But I also need to find height with respect to s, the length of one of the sides. So this is how we can start knocking this thing down. Okay, so let's highlight the piece that we have already. Okay, so we got S equals B, okay, and so I have the area is going to be 1/2, and now I have S, and now I want to find H in terms of S. So there's two different ways that we could do this, and I'll show you both real quick. Is that if I were to just key in on one of this triangle right here, okay, the left-hand side, I could break that into a right triangle, okay? And I can go ahead and say that this side right here is going to be half that amount, 1/2 S, okay? That altitude's going to break that in half. Now, what we can do is that we can use the Pythagorean theorem, okay, to go ahead and solve for H in terms of S. So let's take a look at setting that up, okay? And so looking at this, I'm going to write the next line as the side squared, and I got to square both of these, so that's 1/4 s squared equals h squared. Subtract the 1/4 s from each side, so that's going to give me 3/4 s squared on the left-hand side and an h squared over here. And then I'm going to take the square root of both sides, and I'm going to use the positive square root. Usually we would do a plus or minus, but it wouldn't make sense in this case as it's a geometric figure, and we're not going to have a negative distance here. So the square root of 3 is, well, the square root of 3, and the square root of s squared is just s, and the square root of 4 on the bottom there is going to be 2, so that's what h equals. And so therefore, I can go ahead and say that that is going to be the square root of 3s over 2, and now I can multiply all those together to get the area with respect to one of the sides is going to be, let's see, I'm going to have s times s, which is s squared, the 2's on the bottom, which is going to give me 4, so I would have the square root of 3 s squared all over 4. And this is kind of a neat little formula just to go ahead and have memorize out here, and it may, as your adventures in calculus kind of unfold, you might find yourself better off memorizing that, and it could help you just do some stuff quicker. Another way that we could have found the height is using those special right triangles that we talked about earlier this year. And so we would have, this would be 60 degrees because each angle is going to be 60 degrees, right? And when this one gets cut in half, that's going to make a 30-degree angle right there. And then of course, we have this 90-degree right there. And so, according to special right triangles, if this side is going to be this side, then this is going to be, or the length s, then the longest side is going to be 2s, and the shortest, or I'm sorry, the middle side is going to be the square root of 3s. Now, if I wanted to get just this business of a side all by itself, because this is not two sides, this is just one, right? Okay, I would have to divide each of these by 2, and you can see that in the h position I would have square root of 3s divided by 2, which is what we got from the Pythagorean theorem over here. So one thing that I want to bring out is that notice that we had to do some work to solve for h. And moving into this new school formula that we're going to get using trigonometry to calculate the area of a triangle is going to go ahead and relieve us from having to solve for h to carry on. So let's take a look at how that works out. Okay, so what we're going to do is that we're going to derive how to find the area of the triangles in a whole new way. And so what we're going to do is that we're going to start off with the old school formula and work our way into a new school formula. So let's start there. Okay, so we have area equals 1/2 base times height, which is our old school area of a triangle formula. And so what we're going to do is that we're trying to get rid of that height because we saw in the prerequisite skills there that we were just like, we got to solve for the height, and that can be kind of an ordeal. So let's do this, okay? Is that we're going to start in this position in each one here with this angle A, all right? And I'm going to build both of the formulas in regards to that, and we're also going to go ahead and take a look at how to switch in the base, which we know that is going to be C right here for each one of these, okay? And how to go ahead and get rid of that height right there. So let's start to put the pieces together that we already know. All right, so bringing things down, we would have 1/2. Okay, and the base in this case is going to be, that rhymed, is just going to be that length of C, okay? And then we would still have height, which we know we want to get rid of because it's just kind of a pain, as we saw. So as we're putting all of these things together, we think about, okay, well, how can I tie in height and a known side? Because usually the sides of a triangle are easier to find than the height. You know what I mean? Like this part right here. That's not always the easiest thing to find. But the sides of the triangle, we have many different ways that we're going to learn to be able to find those. So what we're going to do is that we're going to, in each one of these, tie in height to the angle A and that side B. So what I'm going to do right here is that I'm going to write out that the sine of angle A equals h over b. Okay, so it'd be the opposite over the hypotenuse. And likewise, this one on the right-hand side is going to need a little bit of setting up. Since this is angle A and this is a straight line, this angle right here is going to be, and I'm going to have to write this off to the side, 180 degrees minus angle A. So it would be fair to say the sine of 180 degrees minus angle A is going to be the opposite, h over b. Okay? So on the left-hand side, we have, kind of going back and forth, trying to isolate h out of there. We have a pretty easy job because if I multiply each side by the length b, these are going to cancel out, and I'm going to get the height equals b, side b, times the sine of a. And so I can make this switch right in for here, and the new school area is going to be area equals 1/2 c times b times the sine of a. Okay? And to clean this up, I'm going to write area, this is the way that it's typically written, 1/2, okay, b, c, sine a. Not much different. But the way that we're looking at this is the following, and I'm going to this picture right here, kind of get rid of this, and then we'll work on the other one in a moment, is that if you have an angle right here, if you take the sine of that, and you have, it's called an included angle. So angle A would be an included angle, and the sides that make the angle, B and C, right here, okay, and the sine of the included angle A, if you take half of their product, that's going to give us the area of that triangle. Notice that the need to solve for h is gone, which is nice because, again, angles and sides are easier to find rather than the height. Okay. Now, going back to this one on the right-hand side, what we're going to do is that we're going to take a look at this part right here, because we got 180 minus a, and it's like, uh-oh. What does that equal out? And so going back to our trigonometric identities, let's take a look at how to get this thing, that 180 minus a, simplified so we can move on. Okay, so we have the difference formula for sine there that we worked quite a bit with, and if I were to plug 180 in for y, and I'm sorry, for x, and a in for y, I would get the sine of 180 degrees cosine of a minus the sine of a cosine of 180. Okay, so notice that when I start knocking things out, that the cosine of 180 degrees is 0, so that, I'm sorry, the sine of 180 degrees is 0, so that cosine is going to cancel out, and that's going to leave us with a negative sine A, and cosine of 180 degrees we know is a negative 1, so a negative 1, these two negatives are just going to give us sine A. So that ends up working out to be, funny enough, the exact same thing. And that's why the formula is so slick, because it works with an obtuse triangle as well as an acute triangle. So using the same method that we did before, we're going to multiply each side by the base, and we're going to get the same part right here. Okay, canceling these out. And so at the end of the day, we end up with the area is going to equal 1/2 b times c times the sine of a. So that shows that the formula works for obtuse triangles as well as acute triangles. Okay, so let's go ahead and just do one quick example of this thing and see just how we would knock this out. Okay, so since we learned how to go ahead and find the area of a triangle using sine instead of always having to find the height and whatnot, we're going to go ahead and take a look at something kind of neat called the law of sines. And one of the things that is really helpful about the law of sines and the law of cosines that we're going to discover later on is that the triangle does not have to be a right triangle in order for us to go ahead and find the rest of the sides. That is that we don't have to use right triangle trig, Pythagorean theorem, and whatnot to go ahead and knock these things out. So what I want to do is that I just want to do a real quick statement right here that and show you how this works out. Okay, each one of these is a different way to go ahead and in between the equal side, when I say each one of these, this, and this are all going to give us the same answer as far as finding the area of that particular triangle. Okay, so just to show you real quick, the first formula takes advantage of these parts. Okay, so that is one way to go ahead and find the area of the triangle. The included angle would be C, and then using the sides A and B. Another way would be using angle A, okay, taking the sine of it, and then using, so that would be the included angle of the sides B and C, and both of the ones that are drawn out in purple above. And then likewise, the last one is going to go ahead and use angle B as the included angle between A and C. Okay, so all those are equivalent statements, and all of those will give us the exact same solution for the area of those triangles. So, since they are all the same, we can write it as one expanded statement that those are all going to equal the exact same thing, the area of the triangle. So, to derive the law of sines, what we're going to do is that we're going to do something kind of tricky here, is that we're going to take this extended ratio here, or I should say the extended, pardon me, equality there, and we are going to multiply the entire thing by 2a, b, c. 2 over a, b, c, like that. And so therefore, what we're going to do is that we're going to distribute it into each one of these and then see what happens from there. Okay, so when we distribute the 2 over ABC into each one of those statements, we're going to end up with this. And from here, we get to cross some stuff out. So the 2's are going to go out, the A's are going to go out, and the B's are going to go out. So we're going to end up with sine C over side C equals, 2's are going to go out, the B's are going to go out, and the C's are going to go out there, and we end up with sine A over side A, and we have the 2's go out, the A's go out, and the C's go out, and we end up with sine B over side B. So what this basically says, and this is the law of sines right here, is that anytime that we have a triangle, and we usually use this when it is when we don't have a right triangle, is that we can go ahead and use this extended ratio to solve for sides or solve for angles if need be. Okay, so that said, is that in the next video we're going to go ahead and use the law of sines in different cases, and we're also going to go ahead and explore some pitfalls of the law of sines that we got to go ahead and watch out for. So let's go ahead and I'll meet you in the next video. Okay, so we have the law of sines here, and we're going to put it to good use. And so what we're looking for is this business of trying to go ahead and plug in the right parts, take what we need, and then leave what we don't. So in this one, I want to go ahead and I'm going to, and when I say this one, this guy right here, I'm going to use the law of sines to solve for an angle and a side, even though we already know what the angle is going to be, but I just want to demonstrate how we would use the law of sines should we need to find an angle. So let's start off with the side here, and I'm going to start by kind of explaining how to set this thing up. So when you're using the law of sines, what you're looking for specifically is an angle and a side that is across from it, just like we would have the sine of B right here, and the side that is across from it. So we need that condition to be in place, okay? And so I'm going to put then the sine of 29 degrees over the sine of 28 feet there, okay? Now, if I want to find a side here, I will have to go ahead and I'll have to use an angle that is opposite to it. And so I have 102, which is going to be like the sine of C, and a side C, which is an unknown. So what I can do is that I can go the sine of 102 degrees over the side C. So from here, we just use some algebra, the crisscross, okay? And what we're going to do is that we would have crossing, we would have C times the sine of 29 degrees equals 28 times the sine of 102 degrees. And then divide each side by the sine of 29 degrees, like so. And that is going to give us C equals 28 times the sine of 102 degrees all over the sine of 29. And then from here, we're going to have to put that into our calculator, as we don't know what the sine of 102 or 29 is off the top of our head. So what we're going to do is that we poke it in our calculator, and we're going to get, okay, so that's going to approximately give us the length of 56.493 feet. Okay, so that's what the length of C would go ahead and equal. Okay, so what we can do is that that shows that we would be able to use the law of sines to find an unknown side in a non-right triangle, if you will, and it is super useful because, again, we don't need to find like any of these other particular values that break it up in the right triangles or anything like that. We can just skip right to finding the sides. So what I'm going to do is I'm going to erase everything out, and I'm going to solve, even though we know what angle A is right here, but I'm going to go ahead and solve for that just so we can see how to solve for an angle using the law of sines. Okay, so let me reset everything. Okay, so now that we derived that new school formula for finding the area of a triangle, we're going to go ahead and take it for a test drive here. Okay, so what we're going to take a look at is I'm just going to label the sides real quick. We got triangle ABC, where this is going to be little c right there, and this is going to be little b, and this is going to be little a. So what we're looking for, remember, is that we're always looking for this business of an angle, and an included angle, and then the two sides that make up that included angle. And then we just plug it in and let it rip. So it looks like we are going to take sides C and B and the sine of angle A. So I'm just going to write this B times C times the sine of angle A. And so we just drop in the information, and that is really about it. It's a pretty clean process. And so we would have B is going to be 12, and then we got C, which is going to be 10, and then we have the sine of 72 degrees. Okay, and so the area of this triangle, once we go ahead and ask the calculator, is going to be approximately, let's see, we got 114.127 centimeters squared. Okay, super convenient for finding these things out, as long as that we have the sides there. But remember, we have to go ahead and always has to make this shape, and I'm going to just get rid of the triangle for a moment here. So I'm going to cut that out. Has to make the shape that looks like those scissors there, okay? And so you got to have the two sides, and then the angle is included in there. If you don't have that pattern, you can't use it, okay? So that said, let's go ahead and venture on over to a discovery of the law of cosines. Oh, I'm sorry, the law of sines. Okay, now that we have the law of sines derived out, okay, we discovered it, let's go ahead and use it. So the way that we need to plan this out is the following, okay, is that we need to look for this type of scenario, is that we have to have a triangle, and we have to have a set of an angle and the opposite side, okay, being given, and then we need either an angle or a side given. In this case, we got an angle, and then a side that needs needs to be found, okay? So it looks like we're going to go ahead and take a look at this. So watch what I'm writing in purple here. We're going to go the sine of 29 degrees divided by the opposite side, which is going to be 28 feet, equals, okay, and in this case we're solving for a side, so we're going to go sine of 102 degrees all over some unknown value c. So what we need to do then is we need to cross multiply like this, okay, and so it will look like the following. Okay, and then we just need to divide through by the sine of 29 degrees to get c all by itself. So when we divide off on each side, okay, we are going to go ahead and get these guys cancel out, and we'll get the final looking exact answer here for the side C. However, we do want to approximate this out because that is a little bit too nebulous for us to imagine what that is. And so putting it into our calculator, we're going to get, it looks like 56.493 feet, okay? And so that is how we will go ahead and just set up the law of sines for finding a side, just looking for opposites, okay? So we can also use the law of sines to find angles. And so to do so, we're looking for the same type of relationship with an angle that's given and the opposite side. And in this case, I want to go ahead, or the only angle that's going to be available to me is going to be opposite the 7 here, so I'm going to have to solve for angle B first. And once I get angle B, I can solve for angle A and whatnot from there, just using the triangle sum theorem. So let's go ahead and get this thing set up. Okay, so there we go. Making sure that we have the angles on top and the sides there on bottom. And then we could do some cross multiplication, but quality of life thing is that we can just multiply through. Since we're trying to solve for angle B, we can just multiply through by 7 in this case, and that's going to cancel these out. And we're going to get the sine of angle B equals 7 times sine 112 degrees all over 10. Okay. Now, what we want to do is that it seems like we want to immediately put this right-hand side into our calculator. But for accuracy purposes, I encourage you to leave it. And what we're going to do is that we're going to do the same thing. If we're solving for an angle, we're going to say that angle B is going to equal the inverse, okay, like we practiced in previous sections, of this guy right here. Okay. over 10. And we're going to plug that into our calculator, and that is going to give us approximately, so we got B is going to be approximately 40.468 degrees there, okay? So that's how you would use law of sines to solve for an angle. Again, you're just looking for setup, angle across from a side, angle across from a side, and in one of the variables has to be missing. So you need 3 pieces that are known and then 1 piece that is not. So that's how you do that, and it looks like we're going to have to look at, in the next video, one of the things that is a pitfall of the law of sines, which is going to be an ambiguous case, or we're trying to look at using the law of sines to see if a triangle even exists. So I'll see you in that next video so we can decipher what's what. Okay. And so here's the tricky part of the law of sines, and I'm going to walk you through that. First things first is that I'm just going to use this triangle, and you don't have to mark this down. Use this triangle right here. And if you imagine yourself fishing, and this is your fishing pole, okay? And if you imagine that this right here is the water, okay? So what you can take a look at is that with your fishing line, you could have a line that is going to be here, and it could go ahead and swing back and forth like this, depending on if you've baited a fish or not, or just the way that maybe perhaps like your bobber's going back and forth in the water. So why is that an important visualization? And it's important because what we're looking at is that it's a situation where we're given an angle, and then we're given the side that's across from it, which is going to be this little a right here, and then we're given the length basically of the fishing pole, which is going to be right here. And when we solve for the angle B, okay, we don't know if it's going to be an obtuse angle or an acute angle, okay, or it could come out as both. There could be 2 different triangles that we could make from that. We could also have a situation where, and I'm going to erase this out real quick, that your fishing line is too short and it will never hit the water, and therefore it could never make a triangle. So we would be given, again, this angle, this side, and this side, and come to find out that no such triangle can exist. So what we're basically looking at is that we're given information like this up top for something called an ambiguous case. Like, we don't know what's going to come of this unless we run it through the whole cycle of the law of sines and do things with it, which I'm going to teach you how to go ahead and knock out. So let's take a look at setting this thing up and how to go ahead and test for different things where you can have possibility of 1 triangle, no triangles, or 2 different possible triangles. So here we go. Okay, so the first thing that I do is that I label out the sides, okay? And this triangle is just a template triangle, okay? It's not proportional or anything like that. Don't worry about the size of the sides. It's just a visualization for us to go ahead and see if this thing is going to work or not, okay? So what we want to do is that we want to set this up using the law of sines, okay? And we're trying to solve for this angle right here, okay? Because again, we would have, just from the previous video, we'd have this angle, opposite side, and then we would have, of course, this angle in its opposite side. So let's set that up and see where this takes us. Okay, so we have this all set up using the law of sines. And so what we're going to do is that we're going to attempt to solve for angle B. And so we're going to multiply each side by 62 to wipe that out. And then we're going to get this guy right here. Okay, and then we're going to take the inverse sine of both sides to solve for angle B and get approximately, we're going to go, this angle B is going to be 31.47 degrees, okay? Now, that is going to be our acute angle over here. And so, when we have this situation where we have, again, and I'm just highlighting them, angle, a side, and a side given, you know, spells a bad word, that we have to test to make sure that two triangles can't exist, okay? Or I should say, to test if two triangles could exist, okay? So it kind of works both ways. And this is the way that we do it. So that's the acute angle, and I want to make sure that this angle right here, if that exists, B as an obtuse angle, I want to make sure that I include that as part of my potential answer. So the way that I test for this is that I'm going to take 180 degrees, okay, and I am going to subtract from that the 31.47 degrees, and I'm going to get 148.53. So here's the deal, is that this is how we determine if another triangle is possible. Is that if I add the given angle and if I add this angle together, and if it is greater than 180 degrees, because there's only 180 degrees in a triangle, okay, then we know that this triangle, the obtuse triangle, cannot exist. And so therefore, there is only going to go ahead and be one triangle, okay, that, such that is going to go ahead and be like this guy right here, okay? So it's only going to have one solution, and for right now, we just say that angle B is going to equal 31.47 degrees, and that's it. There's no other possible solution for angle B, okay? So let's take a look at what happens for a different scenario. Okay, so looking at this center piece right here and the triangle that's off to the right, I have everything set up. And what I want to do is I want to find the measure of angle B. So let's go ahead and see how, let's set up the law of sines and then knock it out from there. Okay, so the law of sines is all set up, and then multiplying through by 51, we're going to get this guy, and then we're going to have to take the inverse side of both sides to get angle B, which is going to give us, it's going to give us a, oh no, it looks like we're going to get is a domain error, okay? And since we have a domain error, this means is that given these values right here, no such triangle will exist, okay? So in this case, let's go ahead and recap what we've seen so far, is that here we have one possible triangle, okay? In this one, we have no possible triangle. And then we're going to take a look at our final example down here, and I'm going to have to erase some stuff out of here using this information, and I bet you that that is going to be the one where we're going to have two possible triangles. So let's go ahead and take a look. Okay, so labeling everything up, we have this setup here, okay? And so we're going to set up the law of sines and solve for angle B like we typically have done. So I'm just going to cut to the chase and solve for angle B. And I'm going to get 47.56 degrees, okay? So I know that that is going to go ahead, angle B right here is going to be 47.56 degrees, okay? Now, here's the deal, is that I have to check and make sure that this right here, the obtuse part, isn't possible, or is possible, just by doing, again, subtracting that from 180, just so we can check and make sure that another triangle doesn't exist. So far, just to be 100% certain we're all on the same page, we know that this triangle right here exists, where B is going to be an acute angle. What we are testing for is, does a triangle with B being an obtuse angle also exist? Okay, so, or could also exist. So let's do this. Is that I'm going to take 180 degrees, okay? And the reason why I'm subtracting that 180 B from 180 degrees, because this angle right here, if that's true, then this would be B as well, okay? If it were to have that type of symmetry. And so therefore, this angle would have to be 180 minus B. And if that, again, if that's true, if I can add this angle and this angle up and still be below 180 degrees to give me enough angle measure for this angle right here, then I know I can make another triangle. So let's do that. So I'm going to back some of this stuff out, and let's do the 180 minus 47.56 degrees, which is going to give us 132.44 degrees. Okay, so if I take a look at this angle right here, which is going to be the 132.44 degrees, okay, is it possible to have another angle up here? And the answer is yes, because if I add these two up, I take this amount right here, okay, which is this guy, and I add the 40 degrees to that, I'm going to get 172.44 degrees. And so that means is that this angle right here can exist, okay? And I would find that by subtracting this amount from 180, and that would give me 7.56 degrees. So there are two possible triangles. There is possible triangle, the blue one, where B happens to go ahead and be an acute angle. So we would have B can equal 47.56 degrees. Or B could be an obtuse angle from this triangle right here, okay? And that will give me, B could also be 132.44 degrees, okay? So that is one of the tough things about the law of sines. If you go ahead and you have the setup where, again, you have an angle and a side in a side, okay? And so, yeah, it's one of the things that, you know, even though the law of sines is great, you got to watch out for if you do have that pattern. It doesn't come up all the time, but when it does, you do have to check, okay? So, that said, let's go ahead and make our way on over to the law of cosines and see where that takes us. In this video, we're going to go ahead and take a look at just using the law of cosines. And then later on, there will be a video proving out the law of cosines later. But for right now, we got the law of cosines up here, and it depends on what angle that you choose and the position of the sides that are going to go ahead and determine what values to place in for A, B, and C, and then the correct angle that you're taking the cosine of. So let's go ahead and just take a look at its makeup first, okay, rather than going right into the calculations. First of all, is that, and even if I got rid of some values right here, so I'm just going to get rid of these values and come back to them, just to get rid of that, okay, and we'll come back to that in a minute. But notice that about the law of cosines is that angle A right here and this is going to go ahead and have to be opposite, all right, and of one another, and the B and the C, okay, are going to be the included sides, okay, that make up the angle that you're taking the cosine of, okay? So it's always, the makeup is the side that is opposite of the angle, okay? And then all of these B's and C's right here are going to be the sides that are going to make up the included angle A, okay? So that's how you fill in things correctly if you don't have all the A, B, and C, everything already, you know, kind of laid out for you, all right? So let's get started with putting some numerical values to this and seeing how it works. Okay, so here we go. So looking at this, and one thing that I want to make sure that is a common mistake for folks using the law of cosines is that when you're solving a triangle with all sides, which is going to be the first one that we're going to take a look at on the left-hand side there, always start with the largest angle first. Quality of life note is that the largest angle is always across from the longest side. So angle B would be the correct place to start in this particular case. And so this would be the form that we are going to use for the law of cosines because it contains angle B and the sides that we need to make things work in the correct places. So let's fill this out and see where this takes us. Okay, here we go, and looks like we need to. Okay, here we are. Everything all set up. We got the cosine of angle B there, and that is going to be the thing in which we are solving for right now, again, because it's the largest angle, and we have all sides of the triangle that are given. And so what we need to do is that we're just going to clean things up. These are going to be some large numbers here, and so let's go ahead and square some of these out and move them to the left-hand side. So squaring this out, and then we're going to move them to the left-hand side there, and that's going to give us, all right, looks like that's going to give us 101. Okay, and then we have this part that needs to be cleaned up here. So when I multiply those all out, that's going to give me negative 224, and then cosine of B. And now I want to divide each side by negative 224. And that's going to give me the cosine B of, looks like I can't simplify that down, so this is going to give me the negative 101 over 224. And then to solve for angle B, we're going to take the inverse cosine of both sides, so we have B equals the inverse cosine of a negative 101 divided by 224, which is going to give us approximately 116 point, let's see, and so we're just going to call that 80 degrees. Okay, and so, and if you wanted to find the rest of the angles like A and C, you could repeat the entire process using the law of cosines for it, but I just wanted this to show you this example because that's how you would determine an angle using the law of cosines, okay? Kind of a slick thing considering we just have all sides and we're able to go ahead and fetch angles from there. We haven't been able to do that before, okay? Notice that we couldn't use the law of sines with this because we wouldn't have any angles that would be opposite any sides, or I should say any known angles that would be opposite any sides. So the law of cosines we would have to go ahead and use. Same thing with this guy over here is that we would need we have an angle, but we don't have a defined value, and then opposite it, we have an unknown angle and an defined value opposite it, and so we don't have that magic formula of a known angle across from a known side to start us off with the law of sines, and that's why it's important to use the law of cosines in these particular instances. So let's look on the right-hand side and take a look at how to solve for a side using the law of cosines. So for this one, it looks like we're given angle A, so we're going to use this build right here. Okay. And let's fill that in and see where that takes us. Okay, so in this case, what we have to do basically is that we're going to take a look at just putting that into our calculator all at the same time, and then when we're done with that, we're going to get a squared equals some number. So let's go ahead and fetch that number real quick. Okay, now I'm going to leave this number in my calculator, but just for instructional purposes, it's going to be 376 in some change, and so, oops, actually I copied that wrong. It's going to be 29.238. Okay, I was copying the wrong thing down there. And it has a bunch of numbers after this that I'm not showing that's in the calculator there. So what I'm going to do is I'm going to take the square root of both sides, but I'm going to take the square root of it in my calculator for added accuracy, okay? And that is going to give me A is approximately 5.407, okay? So there we go. We end up with A, and that's going to be 5.407. And notice that, and even in both these examples, once you get, if you wanted to go on and find out what the other angles are, this guy and this guy over here, is that you can do so using the law of sines after that. If you feel like the law of cosines is a bit too laborious for you and whatnot, then you can go ahead and switch back and forth to the law of sines, so long as you have now, reveal the information where that's going to give you an angle and an opposite side from that, and then you can solve for the other angles. So that's how you do that. And let's go ahead and take a look at the next problem, which is going to need the law of cosines and a little bit of math 2 skills in regards to parallel lines with it. So I'll meet you in the next video. Okay, in this problem, we're looking at an application of the law of cosines. And so, to paraphrase the problem, we have this structure here that is on the side of a hill, okay? And it is not making a perpendicular, it's not, it wouldn't make sense to go ahead and build the structure like that. And so, therefore, it's straight up and down, and we need to know the length of the wires that are going to be supporting this thing so it doesn't topple over, since it's built on the side of a hill, okay? So what we're looking at is trying to go ahead and fill in as much about the 2 triangles as possible, but one of the pitfalls that we're looking at, since we're trying to find these guys right here, is we have no angular measure except for it's built on this hill that is at a 6-degree incline. So that said, let's take a look at an old school diagram here on the right to see how we can use that to help us reveal some angles. Okay, so if we have 2 parallel lines, okay, and they are cut by a transversal, if you remember this from the Math 2 days, is that you're going to get alternate interior angles. That said, in alternate interior angles, I also should mention that they are going to be congruent or equal to one another. So if I look at this right here, I'm just going to draw some parallel lines. So here would be one line right here, and here's going to be another line that is going to be parallel to it, okay, the best that I can. They're a little bit crooked, but here is the point that I'm trying to make. Actually, I'm going to move this up a little tiny bit here, and so I got some room to draw. There we go. And so that said, is that since this is a 6-degree incline, this angle right here is going to be 6 degrees. So that means is that this little bitty angle right there is going to be 6 degrees as well. Much like with the parallel lines cut by a transversal, the transversal here is actually the ground going through, like so. And so therefore, I know that that little angle is 60 degrees. I'm sorry, 6 degrees. So that means is that if this is going to be a 90-degree angle, because you wanted it to go straight up and down, right? So it's not, again, whatever, the structure is not leaning. So you would have 90 degrees plus 6 degrees, which is going to give us 96 degrees for that angle right there. So in turn, if I'm looking for this angle, I would have, since this is going to be 6 degrees right here as well, because we would have this business of vertical angles right here. Well, basically, let me highlight these a little bit. Right here and right here, those would be the same. And so since that would be 6 degrees, this is going to be 84 because I'd have to subtract that out. And so when I add them up, I know I'm going to get 180 degrees, which is the entire line. They're supplementary to one another, so I know that geometrically I'm good. So I'm going to clear out this picture a little bit so we can start to fill in some more information about the triangles and get to work with the law of cosines. Okay, with the angle measures all taken care of, we can progress on over to some of the sides that we need, and it looks like we're given this one, which is going to be 75, and the height of the tower, which is 100. Okay, so it looks like we are ready to roll. So I'm going to draw these triangles off to the right here and then solve them both separately. Okay, so there is kind of my crude rendition of these triangles. Okay, and so we have first length I'm just going to call X, and the second length I'm going to call Y, and then feed these right into the law of cosines and see if I can get those to go ahead and reveal themselves. Okay, so here are the two triangle setups. Okay, and so let's work on the right-hand side of both those equations real quick. Okay, so there is the right-hand side, and all I did was put it in the calculator, and it did its heavy lifting for me. And so let's go ahead and take the square root of each side, and that is going to give us. Okay, so there's our approximates for the guy wires. Okay, and it looks like it makes sense because the one on the left-hand side is going to be longer than the one on the right-hand side, and so it does pass the first look test and seems legit. So that's going to be it as far as the ending lesson here in this video series. I do plan to release a video in regards to the proving the law of cosines in the next couple days, so go ahead and take a look for that. So all right, I will see you in the next video.